there, this is Teacher Naihma and welcome to another video. Today we'll be talking about molecular geometry. So I hope you have a little bit of a background on this during our lecture, and I hope that you have studied well because we'll be learning how to draw molecular geometries for this video. Now let us review some periodic Now let us review some periodic trends that we have to remember so that we can properly make a geometry. Now let us review some periodic trends that we have to remember. Now, if you remember during our lecture, a column is a group. So for example, you have hydrogen until francium, that is a group, and that happens to be group 1A. Another group would be 2A, which is from beryllium to radium. Okay, and these groups, these columns, they have their special group. Like for example, all those that are red are all alkali metal, and all those that are orange are alkaline earth metals. Okay, so I hope you remember that. Now, each row is a period. So you have period 1 from hydrogen to helium. Period 2 would be lithium to neon. Period 3 would be sodium to argon, and etc., etc. So it just follows. I'm going to transfer my face right here. Okay. Now, how about for the atomic size? Atomic size would increase as you go from left to right. That would be increase. And then it would also increase if you go from top to bottom. Now, how about for electronegativity? For electronegativity, it would increase from left to right, but it would decrease from top to bottom. So these are the things that we have to remember. Okay. Now, let us define some terms. So these are just this is just the part where we review some things that we have already learned during the lecture. So first is electronegativity. What is electronegativity? Electronegativity is the ability of an atom to draw shared electrons towards itself. So it determines the place where electrons spend most of their time in a compound. So for example, you have sodium chloride. So for example, you have sodium chloride. So in this case, sodium would be at the very left, and chlorine would be on the right. So chlorine would be more electronegative than sodium. So a lot of your electrons would spend their time right here in chlorine. How about valence electrons? Valence electrons are the number of electrons that can participate in the formation of a chemical bond. So if you remember what we've learned in a stable, or not really stable, but in an element that has no charge, the number of protons would be the same as the number of electrons. So if it has 18 number of protons, it also has 18 number of electrons. But it doesn't mean that all of these 18 electrons would participate during the bonding of these two elements. So only the valence electrons will do that. And these valence electrons, as I've said, are the outermost electrons, or the electrons in the outermost shell of the element. So these are the number of electrons per group. So it could follow that for the CAS group from 1A to 8A, it corresponds to the number of valence electrons. So if the group is 1A, then there is only one valence electron for that. And if it's group 2A, there will be two valence electrons for that. Now, for the D block, they would follow sort of like the same rules, yeah. But if you look at here, if you see 8b, they would have 3 valence electrons. So all you have to do is just, you don't really have to memorize that. You can just refer to that image if you get a little bit lost when it comes to the number of valence electrons. Now, another thing is the octet rule. The octet rule states that when nonmetal atoms combine to form molecules, they share electrons to have 8 electrons in the valence shell. So that means that when two elements will bond together, they have to have 8 electrons in both of their outermost shells. And how do they do that? They share these electrons for nonmetal atoms. So for example, you have two chlorine atoms. So chlorine is in group 7A. So that means its valence electrons will be 7. So there will be 7 valence electrons and 7 valence electrons. And you can find that in the number of dots that surround each chlorine atom. So if you count that, there's 1, there's 2, 3, 4, 5, 6, 7. So how many not elements, but how many electrons does it lack? It lacks 1. That would be the same case for the other chlorine atom because they're the same element, right? So both of them lack only one valence electron. So what are they going to do? They're going to bond with each other. They're going to share their last electrode. So this chlorine will need 1 electron from the other chlorine, and this chlorine will need another 1 electron from the other chlorine. So it would look like this right here. Now, if you're going to count how many dots there are, that corresponds to how many electrons there are per atom. So chlorine would have 1, 2, 3, 4, 5, 6, 7, 8 after bonding. So there's 8 valence electrons. And then for the other chlorine, that would be 1, 2, 3, 4, 5, 6, 7, 8. Still 8. So you have to count the shared electrons as well. So don't forget that. Now, you would write it, or you would draw it, the bond that is, as one single line. So each single line connotes 2 electrons. So you would count it like this: 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So one line is 2 valence electrons, and if there are 2, that would be 4 valence electrons, and if there are 3 bonds, that would be 6 valence electrons. Now, of course, there are exceptions to the octet rule. First, atoms possessing less than 8 electrons, such as hydrogen, boron, and beryllium, follows reduced electron requirements. Like, for example, hydrogen and helium follow the duet rule. So from the word itself, duet, that means it only needs 2 electrons to be happy. Beryllium follows the quartet rule and needs 4 electrons to be happy, so only 4, doesn't need to reach 8. Boron follows the sextet rule, which needs 6 electrons to be happy. So that's first. Second, atoms possessing odd number of electrons do not need to meet the octet requirements. Most compounds involving nitrogen and other group 5 elements can possess only 7 electrons. These compounds are also known as free radicals. So this is an example of your free radical. This is NO2. Now, if you look at NO2, if you count the number of electrons that are in nitrogen, it will not be 8. Okay, so let's count. This is 2, this is 4, this is 6, and then there's only 1. So 6 plus 1, there will be 7 valence electrons. But does that make NO2 unstable? No, because nitrogen is already happy with just 7 valence electrons. Now third, Atoms possessing more than 8 electrons exhibit hypervalence, where the elements go even higher than 10. Due to their empty d orbitals, elements in period 3 or higher such as p, br, I, xe, and sb can accommodate electrons exceeding 8. So this is an example. This is phosphorus pentafluoride. Now, if you look at phosphorus, how many electrons are surrounding phosphorus? You have 2, 4, 6, 8, 10. Does that make the compound unstable? No, because phosphorus can exceed the 8 electrons required for it to be happy. Okay, so let's start drawing. Before we start drawing, we're going to determine these things, right? So we have here, this is carbon dioxide or CO2. And then we're going to count the number of valence electrons for this compound. So we're going to write here C and O. Now, carbon is in group what? 4A. So it has 4 valence electrons. So 4 valence electrons. And then how many carbons or how many carbon atoms are in this compound? There's only 1. So you just multiply it by 1. Oxygen belongs to group 6. That would mean that there are 6 valence electrons in oxygen. And then how many oxygen atoms are in this compound? There are 2. So you're going to multiply that by 2. So 4 times 1, you'll get 4. And then 6 times 2, you'll get 12. So 12 plus 4, that would be 16 valence electrons all in all. So this would guide you if the geometry that you drew is actually correct. Okay, so let's start drawing. So you know that in this compound, there's only 1 carbon and 2 oxygen atoms. So that will mean that the central atom, you have to determine the central atom, by the way, the central atom would be the one singular. So that would be carbon. But most of the molecules that have carbon, usually carbon is really the central atom. So you have carbon. Now you're going to draw the number of valence electrons for the carbon. So it has 4. So we're going to situate them in such a way that we can place the oxygen in both the right and the left sides, okay? So you're going to draw the dots by pair. So you're going to draw a dot here and a dot here, another dot here, and another dot here. Okay. Now how about for oxygen? You're going to draw them on either side of carbon. Now it looks like carbon is so small. So sorry about that. So oxygen has 6 valence electrons. So we're going to draw that. Okay. Now, what do we need to happen? What do you need? Or how many electrons do you need per atom? So oxygen needs 2. Carbon needs 4, another 4, so 4. And then this oxygen needs another 2. So let's go to the easy part, yeah? Let's go to the easy part. So what if I'm going to donate 2 of my valence electrons to the oxygen on the left, okay? So I'm going to donate 2 electrons from carbon to the oxygen on the left. So how would that look? So first we're going to erase some things, okay? So we're going to erase this and this. Oh, it won't. Why not? Oh, wait a minute. Okay, there it is. So it has been erased, and then let's erase this. And this as well. So we're going to write the other two dots here. Okay, now we're going to donate the last 4 electrons from carbon to oxygen so that oxygen will be happy. So I will write a line right here. So if you look at oxygen, it will be happy, right? So it will get 8 valence electrons. So this is 2, 4, 6, and then 8 here. Okay, so this is already okay. Now, what if we do the same on the oxygen on the right? So we're going to write that here. So if you're going to count how many electrons there are, so you have 2, 4, 6, 8. Okay, that's already 8. So you can just crush that out. But then if you look at carbon, it's still unsatisfied. Why? Because if you count the number of electrons there, you only have 4. 2, 4. So what are we going to do? We're going to donate another 2 electrons from each of the oxygens. Okay, so let's see. Let's donate this one, this pair. Okay, so let's donate that. We're going to crash that out. We're going to erase that. And then we're going to draw a line here. Okay, so let's see if everybody's happy. Is oxygen happy? Let's see. So you have 2, 4, 6, 8. Okay, it's still happy. But what about carbon? Is carbon already happy? Not yet, right? So you get 2, 4, 6. Only 6. So what are we going to do? We're going to donate another pair from the oxygen on the right. Okay, so you gotta delete that, erase that from existence, and then draw another line. Okay, so what do you get? Is oxygen already happy? Yes, it is. 2, 4, 6, 8. Oxygen still happy. How about carbon? 2, 4, 6, 8. All right. So would you say that everybody's happy? Yes, everybody's happy. So in conclusion, we're going to erase all of this. The bond would look like this. So it would have that and that. Okay, so this would be the molecular geometry of carbon dioxide. Now, let's look at some things that we have to identify. We have to identify the number of bonding domains, the number of non-bonding domains, and lastly, the geometry. So if you look at this, let's look at the bonding domains. So how many bonding domains are there? So all you have to do is just look at the central atom. So how many things are bonding towards a central atom? You have this oxygen right here, and then this another oxygen right here. So you would say that the bonding domains, there are 2 bonding domains. Okay. Now how about the non-bonding domains? Are there things, if you look at the central atom, are there things around it that do not bond with other elements? No, there are none. So you would say that for the non-bonding domains, there are 0. So with these information, you can look at what geometry it has. But let's go back a little bit on the valence electrons. So we've calculated earlier that there are 16 valence electrons all in all. So let's count. Are there really 16? So you have 2, 4, 6, 8, 10, 12, 14, and then 16. So that's correct. So you have 16. Now let's go to the chart on molecular geometry. So remember, we have 2 bonding domains and then 0 non-bonding domains. So for the 2 bonding domains, yeah, and then we have 0. Okay, so you would call this geometry as linear. Okay, so it would be linear. Okay, so we're done with the first molecule. Now let's go to the second example that we have. The second example is H2O, which is a molecule that we're very much familiar with. That is hydrogen, dihydrogen oxide, or water. Now let's count the number of valence electrons. So we have H and then O. Now H is in group 1, so it would have 1 valence electron. And then how many hydrogen atoms are there? So there are 2. And then oxygen is in group 6, so it has 6 valence electrons. And then it only has 1 atom for this given molecule. So 1 times 2 would be 2, and 6 times 1 would be 6. So you'll get 8 valence electrons all in all. Okay. Now, what would be the central atom here? So again, as I've said earlier, the central atom would be the lone atom. So in this case, it would be oxygen. And then there are 2 hydrogens. So for the practice, we'll just write both of the hydrogens on either side of oxygen. Now, hydrogen only has 1 electron, so we'll just write a dot here. And then oxygen will have 6 valence electrons. So we'll write that like this. Okay. Now, why did I position it like this? Because I already know that hydrogen is one of the exceptions to the octet rule. Now, if you remember, hydrogen follows the duet rule, which means it only needs 2 valence electrons to be happy, right? So it will only need to borrow 1 electron from the oxygen. That's it. Okay, so what are we going to do? So it's very obvious. So this hydrogen, let's start with this hydrogen. This hydrogen will need only 1 electron. So oxygen will gladly share its 1 electron. So we're going to form a bond just like this. Just imagining that the dots are not there anymore. So there's a bond right there. So hydrogen, is hydrogen happy? Yes, because it has already 2 valence electrons. Now, how about oxygen? So oxygen, let's count. So this is 2, 4, 6, and then 7. So it still lacks 1. Now, how about for the hydrogen on the right side? So you will see that it only needs 1. So what are we going to do? We're going to do the same thing earlier. So we're just going to write or draw a line. So is hydrogen happy? Yes, because it already has 2 electrons. How about for the oxygen? Now, for the oxygen, look at the oxygen. Is it happy? Let's count. So 2, 4, 6, 8. Yeah? Yeah. So that's already, oxygen is already happy. Okay. Now, if you remember in our lecture, we talked about VSEPR, or the valence shell electron pair repulsion theory, wherein if you have lone pairs of electrons, they have this power over the molecule where it sort of repels from the other elements that surround the central atom. So I'll show you what it looks like. But before that, let's count if there are actually 8 valence electrons in total in this particular molecule. So let's count. So you have 2, 4, 6, 8. Okay, so we got the 8, so that is correct. Now, if we're going to be a little bit accurate in our molecular geometry, we're going to follow the Vesper theory. So both of these lone pairs, so these are called lone pairs, by the way, because they don't bond anywhere. So they're just right there. These both of these lone pairs, they sort of they stay on the upper part, and then these bonds, the bonds that we have drawn here and here, they will start to bend. So how would that look like? So let's see. So it would probably look, not probably, but it would look like this one. So you have oxygen here, you have a bond here. Oh, wait a minute. Oh, there's a problem in my whiteboard. So it would probably, I'm just gonna draw at the bottom. I'm gonna move myself right here, the upper right corner. So it would look like this. You have oxygen, and then you have the hydrogens here. Then they have the bond. And then you have 2 pairs of electrons that do not bond. So you would call these as lone pairs, okay? Okay, lone pairs of electrons, and each pair is a non-bonding domain. So let us summarize. How many bonding domains do we have? So how many elements are bonding towards oxygen? So there are 2. That would be 2 hydrogens. So the bonding domains would be 2. How about the non-bonding domains? These are the lone pairs. So how many lone pairs are there? There are 2 lone pairs. So let's look at the chart. So again, 2 bonding domains, 2 non-bonding domains. That would be this one right here. It would be bent. So it would be bent and then tetrahedral. So that is water. Okay, let's go to the third example. We have xenon difluoride. Okay, so xenon is, let's count the valence electrons first. We'll do the same procedure. Xenon belongs to group 8. And then, how many xenon atoms are there? There are only 1. Just 1. And then how about fluorine? Fluorine is group 7, and there are 2 of them. So 8 times 1, that would be 8. 7 times 2 would be 14. And if you add that, 14 plus 8, that would be 22 valence electrons. Okay, now what would be the central atom? And I think that's very obvious. I'm just going to bring myself right here in the bottom right corner. The central atom would obviously be xenon, okay? And then it would be surrounded by 2 fluorine atoms. Okay, so xenon has 8, so it's already happy by itself. But if you remember, xenon is part of the of those elements that can be hypervalent because it belongs in a period that is beyond period 3. So it could break the octet rule. So it could be more than 8. So how many dots should we draw? So we have to draw 8 of them. And then fluorine is has 7. So to make things quite obvious, fluorine only needs 1, correct? So it only needs 1 more. So we're going to situate a dot here and a dot here. So that's already 2. And then you'll need 6 more. So you can just position this right here. Another pair right here. Another pair. Another pair. And then another pair here. So if you count all of those dots, there would be 8 dots for xenon. So 2, 4, 6, and 8. Okay, so this is quite easy. It's not very hard because again, all you need to do is just draw a line between fluorine and xenon, and fluorine only needs 1 more electron. So you just have to draw this line right here, connecting the last electron from fluorine and this other electron from xenon, and then also this one right here. So if you're going to count how many valence electrons there are, fluorine would be already happy because there's 1, there's 2, there's 2, 4, 6, and 8. Okay, and the other fluorine would also be happy because there's 2, 4, 6, 8. How about xenon? Xenon will have 2, 4, 6, 8, 10 electrons. If we're going to count that, will that be a total of 22? So let's see. Are there 22? Are there? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So that would be correct. Okay, so let's look at how many bonding domains there are. So how many atoms are bonding towards xenon? There will be 2. How about for the non-bonding domains? How many non-bonding pairs are there? So you have 1, 2, and 3. So let's look at the geometry. So bonding domains 2, non-bonding domains 3. Okay, so 2 and 3, which would it be? It would be this one. It would be trigonal bipyramidal, but it would be linear. Oh, sorry. Okay, so that would be trigonal, pyramidal, and linear. So all of these purple ones, these would be the lone pairs, okay? So this would be 2 valence electrons, 2 valence electrons, and 2 valence electrons that are not bonding with either of them. So that would be the molecular geometry. Well, let's go to the next one. That would be sulfur hexafluoride. So sulfur would be in group 6. So there will be 6 valence electrons, and there would only be 1 atom of sulfur here. So that would be times 1. And then fluorine will have, because it's in group 7, it will have 7 valence electrons, and then you're going to multiply that by 6. So 6 times 1, that would be 6. Then 7 times 6, that would be 42. So 42 plus 6, that would be 48 valence electrons all in all. So What would be the central atom? So the central atom would be sulfur. Do not be afraid of there are so many valence electrons. That's okay. We can go through this together. Now, fluorine, because there are 6, we'll just situate them like this, like a star, like this one. And then you know that fluorine, since it has 7 valence electrons, how many more electrons does it need? It only needs 1 per fluorine. So let's situate the dots so that only 1 electron will be pointing toward sulfur. It's going to take me a while to draw all the dots. Now, since fluorine will only require 1 more um, electron, if you look at sulfur, it has 6 valence electrons, right? So you just situate the 6 electrons pointing to each fluorine atom. So you don't have to write them in pairs anymore, because you know that each fluorine atom will need 1, only 1. Okay, so let's look at this. So all you gotta do is just write a line, draw a line, and then draw a line right here, then draw another line here, and then another here, another here, and lastly here. So are all of the fluorine atoms happy? Yes. Let's count. 2, 4, 6, 8. And that is true for all of the fluorine atoms. Now, how about sulfur? Sulfur will have 2, 4, 6, 8, 10, 12. Is that permissible? Yes, because sulfur is in the 3rd period. So remember, sulfur is one of those exempted from the octet rule, because one of the exemptions states that those elements that are found in the 3rd period and beyond, they can be hypervalent, or they have the ability to hold more than 8 valence electrons. So this is okay. So everybody's happy. Let's count if there are really 48 valence electrons. So each of it, so 2, 4, 6, 8, and 8 times 6. So 8 times 6 is 48. Okay, so that's correct. Now let's look at the bonding domains. How many bonding domains are there? How many atoms are bonding with sulfur? So there are 6. And how about non-bonding domains? There are none, so that would be 6 and 0. So let's look at the geometry. So which of the following would be correct? That would be this and this one. So the geometry will be octahedral. Okay. And now we're down to, I think this is the last one. Let's see. So we have bromine pentafluoride. So bromine would be in what group? It would be in the 7th group. So it has 7 valence electrons. And then you're going to multiply that by 1 because there's only 1 atom. And then fluorine will be also in group 7, and then multiply that by 5. Okay, 7 times 1, 7, 7 times 5, 35. So you'll get 42 valence electrons. Okay, so which of the two would be the central atom? It would be bromine. And then you're going to situate all of these fluorines in a way like a star. Now this is the concept of this is the same as before because you are reminded that fluorine only needs one more electron. So it would look like this. Now, in this case, bromine will have 7. And then if you take it into consideration the situation of fluorine will only require one valence electron. So you just have to position the one valence electron per fluorine atom from bromine. Okay, so separate that. So you got one here, and then one here, and another here, and then another here, and then another here. But then you have 2 more here. So it's very obvious what's going to happen to these two. So just write a line to connect these dots. And then this one too. Then this one too. And then this one. And the last one. Oh, look at my lines. They're really sloppy lines. So sorry about that. Okay, so let's see if everybody's happy. Is each fluorine atom happy? Yes. So let's count. 2, 4, 6, 8. And that is true for all of the fluorine atoms. Now, what about bromine? Bromine will have 2, 4, 6, 8, 10, 12. Okay, so this is hypervalent. So what does this mean? Is this correct? Is this permissible? Yes, because bromine is in period 4. So this is the type of element that can get more than 8 valence electrons in their outermost shell. So that would be okay. So there are 2 valence electrons in bromine that don't really bond with other atoms. So you see, okay, how many bonding domains are there that connect to bromine? There are 5. So each fluorine atom bonds to bromine. That would be 5. How about non-bonding domains? So this one, only one pair is not bonding. So that would be 5 and 1. So let's look at the chart. So this is 5 and this is 1. So basically the geometry of um, that molecule will be octahedral, and specifically it would be square pyramidal. Okay, so that is it. So thank you so much for watching this video. I hope you have learned something. I hope you have learned how to identify and make Lewis structures for molecules and identify their molecular geometry. This would help you in our next lesson, which talks about intramolecular forces and also the polarity and the non-polarity of certain bonds. So I hope you have a great day and watch out for the next video. Goodbye.